have some fairly focused ideas that we ran through in the lecture, looking at how we're going to determine whether species diversity differs by habitat. We picked up on some really quite big ideas, and one of the big ideas is the idea of samples and populations. We collect data on a sample, and we are hoping we could use data in that sample to make a statement about the population or the data generating mechanism that models the process we think that gave rise to the sample data we collected. We're going to say a little bit about the importance of study design and considering how we measure things, and finally we're going to explain how we set up a null hypothesis in order to disprove it. One of the things we're more specifically going to do, and there will be a walked through demonstration using Minitab, is the two-sampled t-test. So the first big idea is to talk about this population, which is just a piece of jargon to describe the way we understand that data are generated. We believe we can explain everything by some kind of mathematical model, and if we knew the parameters of that mathematical model, such as the population mean, we'd know everything there was to know about that phenomenon. So that, of course, is a simplification, but hopefully we can design things so that it's an acceptable simplification. The second thing we do is that we take random samples from this population and summarize data on those samples by statistics. So key phrases to note here are that we have a population which is described by parameters, and we have samples that are described by statistics. And if we're reading textbooks, populations have Greek symbols, statistics have Roman symbols. The whole idea of what we're trying to do is to follow some procedures called statistical inference that let us use information in the sample to make a statement about the way our data generating mechanism or our population behaves. Measurement is often neglected, but the first thing we have to do is quantify our question. In case of species diversity, there are any number of measures. There's a web link that just lists a whole load of different ways we can collect a load of observations and reduce them to numbers. So there's choices to be made there. It looks like on this occasion we're given the method that we're going to use, but on other occasions we might decide it's more appropriate to use different measures. And the last thing we need to do is to choose a study design, and on this occasion we're carrying out an observational study. What that means is that we don't get to control the treatment that's applied to different subjects. The subjects are wherever the treatment finds them. So in our case we happen to have species on rocks, we happen to have species in pools. We don't get to apply a load of species and see what happens. And to make this really powerful, the most important thing we can do is to use some system of random sampling. So in this case, what are we going to do? Let's make it a little bit more specific. In this case, we're going to pretend that the species diversity per unit area of beach can be modelled as a normal random variable with a population mean of mu and a population variance of sigma squared. What we're hoping to do, we're hoping to eventually show that the population mean is different in the two habitats. Put that mathematically, we're hoping to show that the population mean in rock sites is different from the population mean in pool sites. Notice there's a big caveat. We are assuming that species richness at both has the same variance. So the means might be different, but the variance is the same. In order to do this, we have to set up a statistical hypothesis, and we're looking for a null hypothesis which we can reject. So our null hypothesis is going to be that the population mean in pool habitats is the same as the population mean in rock habitats. And we have statistical procedures that let us tell whether the data in our sample entitle us to reject that null hypothesis. So, Let's set this out all ready for a study. Here is our null hypothesis in formal and mathematical notation. H subscript 0, the null hypothesis, is that mu rock, the population mean at rock sites, minus the population mean at pool sites equals 0. So, we're going to assume that all the observations we get vary around their population mean by an independent random error that's described by sigma squared. As we mentioned, if the populations differ, they only differ in mean, they have the same variance. We're assuming that the normal distribution is a good model, and we're assuming we didn't get unlucky and pick up a couple of gross outliers in our data. So, if our null hypothesis is true, then we would expect the difference in sample means to be 0 plus a little bit of sampling error. What we want to know is the difference in sample means more than the null hypothesis can explain? Is there more difference than given by sampling error? And we could use something called a t-test to evaluate this claim. And the idea of the t-test is that we take the difference in sample means, it's divided by a pooled standard error to give us something called a t-statistic. And our mathematical theory tells us how that t-statistic would behave in a world where the null hypothesis is true. So mathematical theory tells us if the null hypothesis were true, this is what the t-statistic you could get would look like. What we're going to do is to see how plausible our t-statistic is from our sample in the light of this null hypothesis. And the most important thing to note is that we have to set the size of the test before we do anything else, and conventionally we set this to 0.05. So if we find a p-value later on less than 0.05, we're entitled to reject the null hypothesis. So conventionally what this means, the probability of getting a t-statistic from our data that is as extreme or more extreme than the one we got is less than 0.05. So if the t-statistic is either incredibly big or incredibly small, given how we believe the t-statistic should behave, we're entitled to reject the null hypothesis. And the important thing to note is the logic. It's all based on creating infinite virtual worlds where the null hypothesis is true, and then looking at the plausibility of the data against. And notice what we don't do, we don't say anything about the probability of any hypothesis. We just use a decision rule to decide whether we can reject the null hypothesis. So, why the logic matters so much is that if you actually lived in a world where the null hypothesis is true and used this decision rule, 5% of the time you would claim you had a statistically significant result. And as an aside, this is why scientific reproducibility is so important. We need experiments to be reproduced for lots of reasons, but here's one of them. The caveat: if you fail to reject the null hypothesis, it could just be because your sample size was too small. So it's really important to understand the logic of this decision we make. We find the probability of getting data as weird or weirder if the null was true, and based on that p-value, that number, we're entitled to make a decision. Trouble is, I mentioned we make lots of assumptions. What do we do if these assumptions are untenable? Well, one answer that's always possible is to do something called a randomization test. In my opinion, that would be the sensible place to start. The second thing you can do if the assumptions are untenable is to do some kind of maths on the numbers. For instance, if you're counting, it's conventional to take square roots. If you have variables that differ in orders of magnitude, you might want to take logarithms. And you may find, if you do these procedures, the derivatives you get, the logarithms or the square roots of the original data, look as if they behave in accordance with the mathematical assumptions. You could use a non-parametric test, such as the Wilcoxon or the Mann-Whitney test, although you must notice these aren't actually comparing the means anymore, they're comparing the medians. Or, perfectly valid, you could consider your results as descriptive only.